Welcome to The Explainer. You know, we love to take really complex stuff and make it super clear. And today, we're diving into a big one in algebra, factoring.
You know that feeling, right? You're just staring at a math problem, and it looks like a total mess, just a jumble of numbers and letters. But what if I told you there's a toolkit, a way to just systematically take it all apart, piece by piece?
All right, so let's get right into it. What is factoring? Well, at its heart, it's basically multiplication, but in reverse. Think about it. Instead of mashing things together to get some complicated answer, we're taking that complicated answer and figuring out what simpler things made it in the first place.
Just look at this example right here. The thing on the left and the thing on the right. They're the exact same value, but that factored form on the right, it tells us so much more. If you look at the first expression, you can probably spot that, hey, both of those numbers are divisible by 20, and they both have at least one x. So we just pull that common stuff, the 20x, right out front. And what's left behind? Well, 3x minus 2. This new version is a game changer because it starts to reveal the roots of the expression, and that is the secret to solving a ton of equations.
So, if we're building a toolkit, what's the first tool you should always grab? Well, think of a mechanic. They've got that one trusty wrench they always reach for first, right? For us, in factoring, that's the greatest common factor, or GCF. Seriously, you have to check for a GCF before you do anything else. It's step one every single time.
So what exactly is the GCF? It's simply the biggest thing, the largest number and the most variables that every single piece of your expression has in common. It's kind of like the shared DNA that links all the terms together.
And finding it is a super straightforward process. It's these 5 steps you see here. First, you look at just the numbers, the coefficients, and find their biggest common factor. Then, you do the exact same thing for the variables. You smash those two together to get your overall GCF for the expression. Then, you basically divide each original term by that GCF to see what's left. And finally, you just write it all out in that nice, clean, factored form. If you follow these steps, you literally can't go wrong.
Okay, so once you've pulled out the GCF, remember, that's always step one. Your job isn't necessarily done. Now you get to look for recognizable patterns. These are like your specialty tools. You know, not the everyday wrench, but the specific tool for a very specific job.
And here are a couple of the most common ones you'll see. The difference of squares and the perfect square trinomial. Being able to spot these is a massive time saver. It's the difference between fumbling around trying every tool in your box and just knowing, that's the one I need, and getting the job done.
Now for another really cool pattern, the sum or difference of cubes, there's this awesome little acronym to help you out, SOAP. It's all about remembering the signs in your final answer. The first sign is the S, same as the original problem. The next one is the opposite. And the very last one, it's always positive. SOAP. So simple, right? And it works every time.
But, okay, let's get real for a second. This is super important. Just like some numbers, like 7 or 13, are prime and can't be broken down, some polynomials are the same way. You might pull out a GCF, and then that's it, you're done. We call these prime polynomials. And honestly, knowing when to stop factoring is just as important as knowing how to start.
So we've got all these tools now, right? The GCF, the difference of squares, the SOAP thing. But just having the tools isn't enough. You need to know which one to grab and when. A messy toolbox is pretty useless. That's why we need a system to keep everything organized. And that system is the Cornell note-taking method.
I want you to think about this not just as taking notes, but as building your own personal, perfectly organized toolbox. It's a method designed from the ground up to help you do more than just write stuff down. It forces you to actually engage with the material, which makes it way easier to remember and use later.
The layout itself is genius in its simplicity. You've got this big column on the right. That's for your main notes, all the examples, the nitty-gritty details. Then, this narrower column on the left is for your cues, key terms, quick formulas, or even questions you have. And then at the very bottom, you leave a space to write a quick summary later, in your own words. Every part of the page has a purpose.
But here's the thing. Having a great toolbox isn't what makes you a master mechanic. Using the tools is what does it. So the Cornell method isn't just about the layout of the page, it's a whole process for actually mastering the material.
And this is how you turn your notes from just words on a page into something you can actually use. First, you make the notes, then, and this is key, you interact with them. You cover up the right side and try to answer the questions you wrote in the Q column on the left. You literally quiz yourself. And finally, you reflect. After a test, you look back and see what worked. It's this cycle that turns passive learning into a real active skill.
Okay, so let's put this all together. The real master process for factoring isn't just about knowing the math tricks. It's about combining the strategy with a system. You always start with the GCF, your wrench. Then you look for those patterns, your specialty tools. And all the while, you're using your Cornell notes, your toolbox, to practice and make the whole process feel like second nature.
And you know, this is the real secret here. This whole system, having your tools, looking for patterns, and keeping it all organized in a toolbox, that's not just for math. It's a blueprint you can use to break down and master pretty much any complex subject you can think of. So the real question isn't just about factoring. It's, what could you learn if you had a system for everything?